Okay, so let's look at an example of how we might apply these laws to actually calculate a limit. So in this example, we've got the limit as x approaches 4 of the quadratic function x squared minus x plus 3. So let's work this out. So we have the limit. I'm just going to start by transposing what we're actually working out. So we got the limit as x approaches 4 of x squared minus x plus 3. Always start with the limit you're actually working out. Don't just start writing steps partway through the process, right? Take one step to just rewrite the actual limit that you're working on. It makes your work a lot easier to read. And it actually, don't kid yourself, it's easier for you to read as well, not just who you're submitting it to. Okay, so this is the limit we're working on. Now, what property are we going to apply first? First thing we're going to do is apply the property 1 here. That says that if we have the limit of a sum of two functions, we can write that as the sum of the two separate limits, with each function handled separately. Okay, so what are we going to use as our sum? Well, think of x squared minus x as the first function and 3 as the second function. Those are the two functions you're adding together. So if I break this up, I'll have the limit as x approaches 4 of x squared minus x, that's the first limit, plus the limit as x approaches 4 of the constant function 3. Okay, now actually, if you go back here and go back to our first initial observations, we're in a position now to apply this observation, that if we have the limit of a constant, it doesn't matter where the variable x is going. If you're taking the limit of a constant, you're always just going to get that constant back as the result. So here's a perfect chance to use that, because this is the limit of a constant, because 3 is a constant, so this is actually going to be equal to 3. The number 3 does not care that x is approaching 4, right? And then what about this limit here? Well, we can break this up again, because now it's a difference of two functions. We've got a function here and a function here. So we can apply property 2 to split it up as the difference of two separate limits. So let's write this as the limit as x goes to 4 of x squared minus the limit as x goes to 4 of x. So that's really these two limits. If you subtract this limit from this limit, you're going to get this limit. But this one here that was equal to 3, we still haven't added that on, so we'll still go plus 3 now. Okay, and actually now we can knock off a few more pieces here. This one, limit as x approaches 4 of x, that falls under this case here, right? With a equals 4. So if you have the limit of x as x approaches some value, whatever that value is going to be what you get. So in this case, this is going to equal 4. And if we look at the very last rule we wrote on the previous page, if you had the limit as x approaches a of some power of x, you can just take this number a and raise it to the power of n, and that's what you're going to get as an answer. So we can write that limit is just going to be equal to 4 squared. Okay, so what do you get? We've got 4 squared, which is 16, right? So you've got 16 minus 4, which is 12, plus 3 is 15. So we end up getting 15 for this limit. Okay, and it may be worth making note of the fact, and this is not to do with our solution. Our solution is done. This is the actual limit. We're done now. But it might be worth it in hindsight just to think about the fact that if we had just taken the number 4 and plugged it into this function and just worked it out, we would have got 4 squared minus 4 plus 3, which is exactly what this ended up being. 4 squared minus 4 plus 3. So you might ask the question, well, can you just evaluate a limit that way? Because that would have been easier, right? Is it the case that you can evaluate limits by just plugging in these values? And in general, the answer is absolutely not, because that's not what limits mean, right? Limits don't mean what happens to this function when x is equal to 4. They mean what happens to this function as x gets close to 4. Now, of course, there's going to be times when both of those answers are the same. And it turns out that this was one of those functions, that what happens as x gets close to 4 to this function is exactly what happens when x is equal to 4. It gives you 15. So is that always going to happen? And like I said, the answer is no. But it turns out it will always work for some functions. And in particular, this is an example of a polynomial, and actually it'll work for any polynomial. And for that reason, we say that polynomials have what is called the direct substitution property. So that's this first comment here is under direct substitution property. If p of x is some polynomial, then the limit as x approaches a of that function p of x You can work this limit out by just taking a and plugging it right into the polynomial. That's why you get p of a as the answer. So that's the first comment, and this was just a special case of that. So in this case, now that we have this property, if you knew about this in advance, then yeah, we could have evaluated this limit by just plugging in 4. But you can't always do that, so don't fall for the trap of thinking you could do that with any function. The good news is polynomials aren't the only functions you could do that with. Okay, so also rational functions. So let's say if we had some function f, and we could write f of x is equal to p of x over q of x. So let's say p of x and q of x are both polynomials, then that would make f of x a rational function. And so if this is the case, if f is a rational function, and we have some number a that happens to be in its domain, then we can say the following. Then this rational function has the direct substitution property as well. So really I'll write it down first. We have the limit as x approaches a of f of x is equal to f of a. So it turns out that rational functions always have, or pardon me, rational functions also have the direct substitution property, at least at the points that are in their domain, right? This would not hold if a is not in the domain of f, because how could you work this out, right? We never had to mention that for polynomials because polynomials are always defined on the entire real line. Okay, so that's the good news. Polynomials and rational functions have the direct substitution property. You probably couldn't be happier to hear that, because that means if you're dealing with one of those functions and you're trying to work out a limit, it's just as simple as plugging in the point. Okay. So one last remark we're going to put in here. Let's say we got two functions, f and g. So let's say if f and g are not necessarily the same function, but their output values do agree for all x in the vicinity of a or near a. So let's say for all x near the point a. So remember what that means? Remember what it means for something to happen near a point? F of x is equal to g of x for all x near a if the following is true. If you can find an open, I won't draw the picture this time, but if you can find an open interval that has two properties. First of all, it has to contain the point a. And second of all, this condition has to hold for every x in that interval except possibly a itself. This is very much like when we were talking about what it means for a function to be defined near a number a. Okay, this is an extension of that idea. So if you have two functions that agree close to a point a, but they might differ at that point, then we still have the limits are going to agree. So this is very powerful as well. Limit as x approaches a of f of x is going to equal the limit as x approaches a of g of x. Okay, so that's actually a really powerful property as well. And if it doesn't make sense right now, it will when we use it, which is actually going to be in the very next example. You'll see a chance to use this property. Okay, and we're actually going to use property 2 as well when we work out. Actually, pardon me. No, we won't. But in some of the other examples, we use property 2 as well. We're actually going to use property 1 and property 3 for this example, and you'll see why. Okay, so we're asked to calculate the limit as x approaches 1 of x squared minus 1 over x minus 1. Let's work this out. So if I take the limit as x approaches 1 of x squared minus 1 over x minus 1, because that's the limit I'm starting with. Let's start with that. Well, it's a rational function. So you might think, well, hey, property 2 here in this list says that if you have a rational function and a number in its domain, you can work out its limit by just plugging the number directly into the function. So what happens if I do that? What happens if I take 1 and I plug it into this function? I'm going to get 1 squared minus 1, which is 0, over 1 minus 1, which is also 0. So I'm really what it comes down to is just 1 is not in the domain of this function. But it actually is worth mentioning at this point. Let me make a note. If we plug in x equals 1, we get this 0 over 0. And I'm going to put quotations around it because this actually isn't a sensible mathematical expression, but I think we all know what we mean when we write 0 over 0. What we mean is that's what you end up getting if you try to plug the number x equals 1 into this expression. You end up getting 0 on the numerator and 0 on the denominator. Now the reason I'm taking the time to point this out is because a lot of people, when they see that, they immediately jump to the conclusion that the limit does not exist, and they declare that problem finished and then they move on. But that's a mistake. If you ever do that, if you ever get 0 over 0, what that really tells you, unfortunately, is absolutely nothing. It gives you no information. This might still work out very nicely, or maybe it doesn't exist. But if it doesn't exist, this is not the reason. The fact that we plugged in 1 and got 0 over 0 does not tell us that that limit doesn't exist. Unfortunately, it doesn't tell us what to do either. But all it does tell us is that if we want to solve this problem, we're going to have to try something else. So let me finish that thought. So if we plug in x equals 1, we get a 0 over 0 type. Let me finish the thought, which is called an indeterminate form. Okay, and I think I'm probably spelling that word wrong. I forget if it's indeterminate or indeterminate. I might have to correct that later. But in any event, that means you have to do more work, which means more study is needed. That's maybe just a weird way of saying you need to go back to the drawing board and try something else. Okay, so let's try something else. Can we do anything else? Well, notice that the numerator is x squared minus 1. So we get the limit as x approaches 1. X squared minus 1, that's actually x squared minus 1 squared, right? So we actually can write this as x minus 1 times x plus 1. Because remember, x squared minus 1, that's x squared minus 1 squared, and that's a difference of squares. So we can write that as x minus 1, x plus 1. So that's just a separate note there. Okay, so let's finish this off. So we still have x minus 1 on the denominator, and hey, it looks like I can algebraically cancel the x minus 1s there. I can actually reduce this fraction because I have a common factor of x minus 1 on the numerator and the denominator. So I get the limit as x approaches 1 of x plus 1. But now, let's wait a second. Why are we allowed to do this? Yeah, okay, we can cancel the x minus 1s, but that's something we do when we're doing algebra. And this function here and this function here aren't actually the same function, technically, because this one is defined when x is equal to 1. I can plug 1 into this function. But I can't plug 1 into this function because I'd get, the denominator would be 0 if I plugged in 1. So this function and this function are not actually the same. So why are we allowed to say that why are we allowed to jump to the conclusion that their limits are going to be the same? Because that's what I've done by writing this equal sign here. Well, that's where property 3 comes in, right? This function and this function aren't actually the same function, but they do agree for all x near the point 1. Because the only point at which they don't agree is actually the point x equals 1 itself. But then you've heard me say this lots, but remember, the limit does not care what happens when x is actually equal to 1. So we can safely cancel these and instead now work with the function x plus 1. And hey, guess what? X plus 1 is a polynomial. So it has the direct substitution property by the first statement. So we can just go ahead and plug in 1, and we'll get the limit as x approaches 1, or pardon me, if we plug in 1 here, you're just going to get 1 plus 1. And that's going to be 2. So that's your limit. The limit ended up evaluating to 2. And just for good measure here, now that we're getting into the more calculation type problems, it's probably a good habit to reinforce here. Let's get in the habit of putting a box around our answer to kind of signify that the calculation is complete. Okay, it makes work so much easier to read and follow that way. Okay, so it's a good thing that when we saw the 0 over 0 type, if we plug in the number x equals 1, and if we just try to plug it in at this stage and we got 0 over 0, it's a good thing we didn't just assume that the limit doesn't exist. So just because you got this doesn't mean anything. It just means that that strategy won't work. Okay, so another example. We've got to calculate the limit as h goes to 0 of 3 plus h all squared minus 9 over h. Okay. Remember when we mentioned at the very beginning of the previous problem that we plugged in x equals 1 and got this indeterminate form of 0 over 0? It's a good habit to just do that at the very beginning of every limit problem. It's always worth just thinking about, right? It doesn't mean that's going to be how you solve it. It doesn't mean that's going to lead to a solution, but sometimes it might. So it's always worth just, even if you don't write anything down, just mentally run through the process. What would happen if we just plug this value into the function? It's a function of h, and we're taking the limit as h goes to 0. What happens if I just plug in h equals 0 to this fraction? Well, I get 3 plus 0, which is 3, squared, which is 9. Subtract 9, you're going to get 9 minus 9, which is 0 on the numerator. And then, of course, if you plug in 0 for the denominator, you're going to get 0 there as well. So it would also be a 0 over 0 type. Okay, that doesn't help us. But it's just worth checking at the beginning, because we might have gotten something else which might have given us some insight on what to do next. But since we got 0 over 0, we just have to go back to the drawing board and accept that that's not going to help. Okay, so what do you do in this case? I would say probably what you want to do is, well, if we expanded these brackets, we'd have a quadratic, and then we could maybe combine like terms with the minus 9, and maybe something nice would happen, right? That's always a possibility, and in fact, in hindsight, you'll see that that's exactly what happens. So, but that should be one of your tricks that you have in your tool belt for working through limit problems. If you see a polynomial that's, if you see a numerator that is, part of it is a factored polynomial, and then you've got some other piece of a polynomial there as well, it might be worth expanding everything out and combining it to see what happens, because sometimes simplification will help, like it does in this case. Okay, so let's work this out. We've got the limit as h goes to 0 of, just copying down our problem, 3 plus h all squared minus 9 all over h. Okay, so let's square the brackets and see what we get. So we get the limit as h goes to 0 of 9 plus 6h plus h squared. That's what you'll get if you FOIL out the brackets. FOIL them out carefully, right? And you'll end up getting this expression. So then we'll subtract 9, and this is all divided by h. Okay? Great. Well, what happened? Oh, hey, here's a positive 9 and a negative 9. They're going to cancel out perfectly, and we're going to get the limit as h goes to 0 of 6h minus h squared all over h. Okay. And now, actually, now that we've combined everything, we could even factor again now, because the numerator has a common factor of h. So we could factor out an h, and we get the limit as h goes to 0 of h. This should have been 6h plus h squared, shouldn't it? And so this will be h times 6 plus h all over h. So now we can cancel these h's. That worked out nice. Just like we canceled the x minus 1s up here. And what are you going to be left with? I'm not going to quite have enough room to finish on this line, so I'm going to work downward from here. I'll say this is equal to the limit as h goes to 0 of 6 plus h. And then now, 6 plus h, that's a polynomial in the variable h. So it has the direct substitution property. So we can just take this h equals 0, plug it in, and we're going to get 6 plus 0, which is equal to 6, finally. Almost went off the screen, but that's what you're going to get for this example. So then we can put a box around that. That's our final answer. Another comment I want to make before I flip the page, and here's what it is. Notice that I wasn't just doing this for fun, by the way. Notice that every single step I wrote limit as h goes to 0, limit as h goes to 0. I wrote it on every single step, and you need to do the same thing. Pardon me, you need to do the same thing yourself. Because when do you stop writing the limit? Notice that I did it on this step. It's when I apply the direct substitution property. It's when the limit actually got taken, right? So that's when you want to that's the only time you want to stop writing the limit is when you've actually taken the limit. Notice up with this example here too, I wrote limit as x goes to 1, limit as x goes to 1. I wrote it here again as well. But when did I stop writing it? Was between this step and this step. That's where I didn't write it again, right? Because the limit was actually taken from this step to this step. The direct substitution property was applied. So that is when we stopped writing the limit on this example. So watch out for that. It's a lot of people come up with a habit early on is they kind of just get lazy and they decide that it's too much work to write this, so they just don't bother, and then they just kind of try to keep track mentally of the limit that they're actually taking. But that's not what you want to do. You want to write your steps as precisely and carefully as you can. So always keep writing this until the point at which you've actually taken the limit. So in this case, it was here.